You're okay. All right.
Yeah, please go ahead.
Great. Hi everyone. Thanks for joining. We have a presentation today on structural integrity and how we arrived at this, how we arrived at this state. Our presenter primarily is Dr. Alan Geary, and I'm not Dr. Alan Geary. Dr. Alan Geary and I work together, and he's my partner. He's in Australia, and he's online right now, but he's having technical difficulties. So, in any event, I'm going to get it started. And unfortunately, he's the one who really knows how to do this quite well. He prepared these slides, so I'm going to do the best I can until he does actually join. So, let's see. Is everybody able to see these slides? Can anybody give me the thumbs up? I think we should be good. So I'm going to take that as a yes. So, well, welcome. And we're going to talk about structural integrity. To do a little background with Dr. Geary, Dr. Geary had his career start in the UK, and he had a very interesting career. That's why these slides are specifically poignant and specific to structural integrity. It's because he had an entire career associated with this for some 55 years. And he worked with the electricity board in the UK and figured out some of their problems with electric generating plants and more on in the way of structural dynamics and how those facilities operated. But then he got into the BRE, the Building Research Establishment. And that's really kind of almost an equivalent version of NIST in the United States. And he worked there for a couple of decades, got a PhD and a higher doctorate there, was awarded the Telford Gold Medal, and it was all for his work on shaking structures. Basically, he got a vibrator system and he shook large structures, and the purpose of that was to understand structural integrity, which at the time was called structural adequacy. The same topic. So his career bookended this issue that is so poignant right now, because structural integrity is an operative term. It's now legally mandated. It's defined in ASCE 7. ASCE 11 gives methods for assessing structures. And there's a lot of other aspects of the code. The International Building Code has testing methods to verify structural integrity. ISO standard 4866 is about testing structures for structural integrity. So there's a lot to know, but there's also a lot of history. So this course is about structural integrity through the ages. We have about 10 slides on it. Health monitoring of structures, collapses and lessons learned, collapses missed in the US, the Champlain Tower, the new legal approach, and the future of condition assessments. So in the ancient world, you had master builders and military domination. Uh, Structural design by stonemasons and carpenters. They principally did visual inspections, and very ironically, that's kind of still what we do now. Really should advance that. Technology advanced in the Roman Empire, and you can see that with some of the arches in Europe and aqueducts and things like that. The Romans were really pretty good at building things. Many of those things are still around. Um, the original approach to structural integrity, from the design side, you had solid and stiffness overkill. So they made things really robust, big, giant, massive structures. Mass would keep them together, they believed. Interestingly, the concrete from the Roman times is actually far superior to what we have now. A lot of it still is around based on using volcanic ash. Um, the Romans created domes and vaults and arches and things like that. And there was a lot of ingenuity involved in that, keeping everything under compression. The foundations provide a reactive force. For maintenance, they had self-repairing concrete. As I mentioned, that's due to uh, the ash used by the Romans. It's really pretty ingenious. Impinging forces based on experience. They kind of figured it out as they went. I'd like to see how many things actually fell down because they didn't get it right initially. I don't think they were going through steep calculations and have huge factors of safety, but they knew when it worked because it stayed there. User requirements, users required to adapt to structures. Um, so moving on to the Renaissance, in the 14th to the 17th century, there's a link between medieval and modern times, the Enlightenment, focusing on classical Stoicism, human potential, and literature. Again, these were created by Alan, and I wish he was here to give them, but he has more insight into this classical era. Artistic innovation by Da Vinci and Raffaello and Michelangelo, a move away from purely religious workings. So different inventions, the Gutenberg printing press revolutionized communication. That was really actually an amazing thing, a stepping stone for humanity. Um, uh, so heliocentric model allowed for worldwide travel and colonialism. End of the era with religious reformation and shifting political ideas in the Baroque era, extravagant art, music. So a lot of interesting things happening during the Renaissance. Um, the Enlightenment required that laws be rational, uniform, and acceptable. And Royal Society, Dr. Geary is a member of the Royal Society, actually started in the 1660. So they really started embracing science and institutionalizing it. John Smeaton was the first civil engineer. Separation of architecture and engineering in the West occurred. So in the 1700s, we start seeing the first school of engineering, 1818, the Institution of Civil Engineers in London. So now we're starting to approach modern times, and this was during the colonial era in the US. It's very interesting if you go into New York, where we really got started. They started building a lot of buildings, tenements, and whatnot in the 1800s. And a lot of the codes that were used and the design standards came from the UK. And they looked at, you can look at the historical evidence, 10, 15 pounds per square foot was a design requirement. So all of these older structures were built to withstand some forces. And Dr. Geary says 1852, the ASCE was formed. So, from that point forward, it was incremental steps in code evolution. So, um, 450 BCE, the Roman law, 12 tables consolidated traditions into law. Emperor Justinian, his civil law of Rome of 6th century CE, addressed structural issues. Denmark and Sweden had the first national codes. So that's interesting. The Prussian law, 1794, attempted to codify all these laws. The Napoleonic era, 1804, and the German codes influenced much of the rest of the world, as did the UK in the 1800s. So there was always been some interaction between countries. Alan and his background, he did quite a bit of that. He actually participated in the codes on all 5 continents that have people on it, that is. He worked in Asia and Europe, the US, Australia, New Zealand, and South America as well. So he's impacted all those codes. So um, changes that influenced since 1900, allowable stress design early on, designed for composite action, reinforced concrete in 1902. Then we started in 1950 to 1970, addressing load factors, dead and live load, limit state design, ultimate and serviceability, the start of standardization and awareness of dynamic behavior. And this really matters. Actually, I think it was 1972 where we had the San Fernando earthquake. And that was a big game changer. I think in 1906, they had the San Francisco earthquake, and the response to it after San Francisco was destroyed was that they doubled the pounds per square foot. They went from 15 pounds per square foot as a stiffness requirement to 30. So that was interesting. They just added more stiffness, no ductility. So there was quite a bit of figuring it out to do. But during this time, they started to look at dynamics after several earthquakes and the Tacoma Narrows Bridge failure. That was a big factor as well. And then in the 70s to the 90s, you had probabilistic using return periods. And that happened globally. There was a lot of interaction. Alan was very involved in that. But using return periods for wind and seismic events, structural reliability analysis, more uniform codes. They started nationalizing them broadly. We had BOCA back then, and that was broken up into 4 groups, and now we have the IBC. So now, currently, we have performance-based design, limits on performance, maximum displacements, structural health, life cycle management, resilience, looking for survival of extreme events, and holistic assessment. It's interesting. I was looking at something last night on one of the Discovery channels, and they were talking about Japan and that they've upped their codes going back to the 80s to make sure that buildings could not only withstand an earthquake, but be good for occupancy and use. We didn't do that in the US. We just said, just don't let it kill people. So you might destroy the building, but don't kill anybody. So we're evolving here as well, updating our codes, and there's a give and take with the economies of it and whatnot. So factors of safety, it's an interesting thing because how do you verify it? Oops, sorry. Let me go back to that. Um, Materials are still very variable, but back then they certainly were, especially cast iron. Safety factors for allowable stress was 4 in the 19th century, commonly known as a factor of ignorance in the 1960s, which is a good one, and not all that inappropriate. I think a lot of people feel very safe having a big factor of safety, whether it's 3 or 4. 3 is kind of standard engineering practice, maybe 4. But you kind of say, well, they had a lot of factor of safety. But when you get things that degrade, that goes away real quick. And being able to measure these things is relevant. Rolled steel was introduced in the 1880s. Some of that steel from the 1880s, is actually much far superior to what we have now. They really did a good job back then. Early bending stress safety factor was 1.7. Post-war permissible stress design, permissible bending stress, 10 tons per square inch for the Tay Bridge disaster, which infers a factor of safety of 1.65. If you're not familiar with the Tay Bridge disaster, that was what really got started in terms of codifying wind requirements, because that bridge was a big failure. It was a big deal in the UK, and it really created a big upheaval within engineering. And we got to limit state design, safety factors similar to permissible stress. In modern codes, we have safety factors that are approximately 1.4. And that's just a multiplier on the expected loading. Now we have digital twins, pressure to reduce factors of safety. So I don't know if that's a real good idea. Very interesting. In our line of work, we measure the capacity of structures, and we see that the older structures, the Roosevelt era ones, are very, very robust. And then there was a dip in the 50s, and I think people got pretty aggressive with how they added kind of advanced engineering analysis and tried to limit section and things like that. But a lot of those structures we measure from the 50s and 60s have issues, and they're starting to really hit their age right now. So, and then we started tightening it up again. So there's kind of, in our opinion, a dip. We see a lot of buildings of that era that have some issues. Structural integrity definition. So this is really important. This term, structural integrity, is defined in ASCE 7, and we have it. It's chapter 1 of ASCE 7. So you can go in there. 1.4 defines exactly what structural integrity means, and it tells you exactly the loading minimum loading that you have to have, that forces are supposed to be distributed. So we have that definition coming up, but a general definition is the ability of a structure or any of its components to perform its intended function by safely supporting and transmitting all applied loads to the ground without experiencing collapse, excessive deformation, detachment, or loss of function. So it seems common sense, but I think structural integrity is a term that everybody has their own definition. And it is defined in the codes, and that's what we as engineers should be using. So here are some other lessons, as I mentioned at Tay Bridge in 1879. So treating wind as a steady force. A lot of lessons were learned by this. Tragically, this train came off and went into the ravine and killed a bunch of people. Um, and it was a fatigue-related issue, what they found out. Framingham was a building that collapsed. Again, it was very common to things that happen now: rush to finish, poor design, lack of knowledge of required dead loads. Ferry Bridge in 1965 happened in the UK. Those were big cooling towers. We've assessed those as well. And winds came and excited dynamic behavior. They were under-designed. It says misunderstood construction. Alan Davenport, he did a work on the dynamic nature of wind forces. It was all around this time. It was an advancement for wind engineering. That's when Alan started getting his start in the industry. So this is a really important one. This is still referenced in ASCE 7. Ronan Point is seen as the beginning of structural integrity. It was a progressive collapse from 1968, and some lady in one of these apartments was boiling tea. She had a gas leak. It exploded. It blew out a wall, and this was a manufactured building, and it created this progressive collapse. The unfortunate thing was it was a poor construction model. They expanded it, made it higher than it was recommended. It was made of precast panels, and Allen and his team went out and measured it in 1984. They actually shook it with vibrators to understand the mechanism of damage. And pretty powerful body of work to be able to go out there and measure things for their capacity. So like I said, it's still referenced as the beginning of structural integrity. So look for yourself in ASCE 7. As the codes developed, really 1879 with the Tay Bridge was when actual wind loading of 15 pounds per square foot came in. The San Francisco earthquake, that was a big one, and they went to 30 pounds per square foot back then. If I said inch, I meant foot. And then we had the Tacoma Narrows Bridge, which everyone is very familiar with, and we got into prescriptive codes. And 1989, NIST and the National Science Foundation they were looking at performance assessment goals. So we got to a point in our society where the government had said, listen, we've had enough failures. We know things are degrading, and we got to start looking at risk, changing risk profiles, and put together technologies that work. So in 1989, they came up with a bunch of recommendations on different ways to validate structural integrity. There were dynamic measurements and mode or model calibration and a lot of different things. And now we're looking at risk and performance progression. So design standards are looking at performance, and there's performance-based design in ASCE 7. Some other collapses missed in the U.S. Department store in 1995 in Korea killed 500 people, and the owner was jailed. In other countries, especially the Asian countries, they're much more rigorous about holding the engineer accountable. You can go to jail in other places. Here, you kind of go to court, but you pay, your insurance company pays. But over there, it's a whole different animal. So the Rana Plaza collapse from 2013 in Bangladesh, that was tragic. I remember when that happened. And 1,300 people died. That's a tragedy. And that was a weak building, and they just overloaded it. And they had a lot of machinery in there, and it just eventually collapsed. but a lot of different countries have questionable codes. It's another reason, a justification for doing measurements on structures to objectively assess them. Because a lot of times these buildings get patched and you can't tell by looking at them if they've lost capacity. A lot of times just before the engineer comes, they do that sort of patching. As a matter of fact, for the Champlain Tower, that was one of the criticisms that the investigation showed was that the inspection program they had didn't have any testing, none. And people were just mailing in assessments, from what I've heard, and what was validated in that investigation. So, we've got to get to a point of getting more accurate and effective inspections. So, this building collapse, Magnitogorsk building collapse, 10-story building in Russia due to a gas explosion. I didn't know that one. So Alan knows a lot of things that I don't know. But this is the one that we all know, was the Champlain Tower in Surfside. It was a 40-year-old building, just about. Was 98 people died, $1 billion loss. And what happened with this in 2015, they estimated that the repairs were $6 million. There was significant damage, and they knew it. And the engineer, a lot of it gets patched, and he didn't really know how to assess it effectively. By 2020, they estimated it to be 15 million. So in 2 short years, the degradation accelerated. And that's the problem with degradation. That's what people have to realize, is that it's not linear. Just because you had a little degradation this week, in a year, you might have, 3 times that. You get chemical changes, you get chlorides hitting steel, they blow out the concrete, and it can look drastically different very quickly. It can be perfectly fine for 40 years and then look really bad really quickly. And that's what was happening there. And, the engineer's not on site all the time. So we advocate for monitoring structures like that. And it makes a lot of sense. Engineers need those sorts of tools. In June 24th, 2021, this building collapsed. It was a partial collapse, but a significant portion of the building. NISTA has done a study on it. It's very interesting. If you want to read it, you should. But they hadn't started. They were about to start the repairs, but they hadn't. The report was that the pool disappeared, which is right around here. And when they say the pool disappeared, something collapsed. So they had the deck had collapsed, dragged the pool, and the pool went underneath into the parking garage. All the water probably didn't do much good down there. And what it appears to me, there was a drop beam that was monolithic with the pool deck, which created a rotation of that beam and created the progressive collapse. So it's tragic when things like that happen. But when you see the damage that had occurred, it you have to think about the potential of a progressive collapse or subsequent damage that can occur if something goes bad. But there was quite a lot of degradation in this area here. There were shear cracks right around the columns, and it was pretty noticeable. These next 4 slides gonna show you how the center of this building came down. And like I said, you had the pool over here, and it pulled on a drop beam, and it pulled this section down. And you can see it moving down the penthouse floor, going down. And I'll do that again. So look again right here in the center. You'll see this section go down. It's moving there. It kind of messes up the view. And it's going down further. So the whole thing collapsed in the center, and then it pulled down this side as well. This side remained, but pretty tragic. There were signs from the deck top, so I don't know. Would any good engineer have made a lot of noise about this? So, you had these lateral shear cracks, severe stress in the deck at least 3 weeks before the collapse. And you got to do something at that point. You got to put some form of monitoring on something that has this level of damage. And there was so the way this pool deck worked, I think it was 6 or 8 inches of concrete, and then they had sand and they had these pavers on top, and there was an impervious layer that failed. So that impervious layer allowed the salt water to get in and degrade this concrete. And pretty soon it was just around that column, it was just hanging on threads. And so this started moving, everything started moving. And, pretty soon, I believe there was a punching shear on that column. So, again, tragic. But there were signs up top. I think you'd seen, a lot of people have seen cracks like this in other locations. You really got to take a look and do a deeper investigation, whether it's with, concrete corings, dynamic testing, what have you.
But can you see
Yeah.
the note in the chat, please?
No, I don't see him. Hi, Tom. The issue is with you using Alan's login is why there maybe he can't join. Then when you can join, please take a break. So what do I need to do?
Take a break so and leave and he join and then with your login and Alan can join with his login.
Okay. So I need to get out or what am I doing?
Yes, yeah, just take a break, 5 minutes, 2 minutes,
Okay.
and we'll try see if Alan can join. And in your email, you will have the Zoom link to in your
Okay.
email.
So
So
you want me to physically leave?
yeah, like log in, log out. So let's take
Yeah.
2 minute break for
Okay.
everyone so we can resolve this because we like Alan to join. We can.
Yeah, no, absolutely. I don't want to
Okay,
do this anymore.
so let's do that.
Okay. Hisham is Alan on?
No, he's not, and it shows his name, not yours. So I don't know
So I'm back using his
for
login.
some reason.
So
For some
I'll
reason.
yeah, I'll try to get out. I'll get out again. Sorry about this.
No,
Yeah, I don't have another invite. I just have the one invite and
no,
it's
I just resent it again from Zoom.
you've resent it.
Yeah.
I didn't get an email on it. So I'll get out and try to let Alan get back in. Sorry for this, gang.
There you go. There's three of
All
you.
right, we
Okay.
go. How you
Hi,
doing,
Alan.
Alan?
Hello, Hisham. Are we all okay now?
Yeah. Well, you can see what time it started, and he can load his, tell you where
Leave,
we are.
leave
And
the other one as well.
Yeah, Alan, I got to about slide 21 for the Champlain Tower. But if you want to do a quick recap, like a 1 or 2 minute, I did the best I could with the history. I wasn't prepared for that, so I thought you would run. So
It's okay. It's all right, Tom. Um, in fact, if one or two slides of Champlain are missing, it doesn't really matter because we can talk through that.
yeah. I got the slide 21 if you want to take it from there or whatever you think, but you run with it and I'll let you go.
And let me see. You're going to give a bit of an introduction, and let's see where slide 21 goes to.
Yeah. I already did the introduction and I went through slide 1 through 21. So you can just pick it up during Champlain
Yep.
Tower.
Okay.
You
All right.
can,
That's fine.
yeah, feel free to start wherever you like, but that's where I got.
Okay, Tom.
Very good.
No problem. I can handle whatever's necessary.
Okay.
I had a COVID and flu injection yesterday, and I have a high temperature this morning.
Well, that's no good.
Fingers crossed it'll be all right, but be ready to take it over if necessary.
All right. Have at it. Yeah, you'll have to run the slides, Alan.
Sure thing.
Alan, you're presenting now. Are you ready to go?
Okay, all right.
Yeah, people waiting.
Really?
Yeah, there's 9 people on. We're in the middle of a presentation.
Okay, all right. I thought that we were starting at 3 o'clock.
It's 3:40, 3:34 right now. You're a half hour late.
Oh, okay. All right then. So, good afternoon, ladies and gentlemen. Um, this is Alan Geary and Thomas Wynant, and we are going to give you a presentation on structural integrity and how we arrived at the current legal status. So let me hand over to my Thomas Wynant, my colleague Thomas Wynant, who will give you an introduction.
Alan, I've already done that. I actually done a pretty lengthy description of your background and what you've done in your career, and yeah, went through the
Oh, okay.
BRE. So yeah, we're good to go. You can just jump right into the slides.
So slide 21.
You'll have to share them with everybody, Alan.
Yeah, yeah, sure. Ah, And the slide, the tag for share.
Alan, right on the bottom, if you move your cursor on the bottom, you'll see, you'll see it pop up and it'll be a share button there. So can you drag your
Yep.
cursor?
Uh,
You see share there?
Okay, I got it now. Sorry about that, ladies and gentlemen. We had some little bit of messing about there, but I think we're okay and we're going now.
Yeah. Okay. Just put it into slideshow mode and you can do
Yep.
21 there.
Okay.
So yeah, if you want to back up and talk about, the progression of that. Yeah, so
No, that's okay. If you've been talking about that, then that's fine. And in fact, if you've gone on about Champlain, this next picture, which is 22 in the slides, actually shows a picture of what happened near the swimming pool and a big horizontal crack. Now, what will happen is somebody is having a look to see if they can find an idea of something which is not quite right. You might just walk past this the sort of thing. However, in fact, it was particularly important. A horizontal crack is an indication of stresses in that area. So the immediate response after Champlain was building has got to be safe, and condominiums must be protected against collapse. And inspection for structural secrecy is a must. And on top of that, we must have a reserve fund, and inspection after a specific age is required. Additionally, we could modify ASC 11 and structural ASC 11, ASC 7 has a definition of structural integrity. Many codes have actually said, okay, so long as we have that definition in there, then we don't need to worry too much. And this is it. All structures shall be provided with a continuous load path in accordance with the requirements of section 1.4.1 and shall have a complete lateral force resisting system and with adequate strength to resist the forces indicated in section 1.2. In other words, the forces must be, the structure must take care of the forces which will appear on the structure. And so ASC 7 says you need to do that.
hey, Alan. Alan?
Yes, Alan.
I think maybe I'll just take over. Okay. I think the shots probably affected you a little bit.
Yes, okay. You go,
Yeah.
Jim.
Let me run with it, okay?
Okay.
So to pick up where Alan left off, and I mentioned this. This is section 1.4 of structural integrity. It's in ASCE 7, the 7-22. As Alan said, it requires a continuous load path and a complete lateral force resisting system. And this is really important because fundamentally, how do structures behave? Well, they've got to take forces, transfer them, and get them down to the ground. And they got to distribute them evenly. And they also got to have enough capacity. You got to meet life safety requirements. So the idea of structural integrity isn't just that everything's tied together, it's tied together and functioning effectively. So a structural integrity assessment require the requirements for testing structural integrity, collapse prevention, consistent with the design, sufficient reserve funds to afford maintenance, and professional and legal elements. So this is what's happening in the US. Florida passed their structural integrity law. New Jersey passed theirs. Now Virginia has one. Maryland has one. I believe Illinois has one. There are laws in different cities as well. I think there's 11 states. Freddie and Fannie now have it in banking. And they all reference the term structural integrity. And structural integrity is the operative word. So it's really, really important to understand what it means. And again, it's right in there, 1.4 of ASCE 7. So some of the performance requirements that are into code now, and this is really a paradigm shift in the industry. It changes everything for everybody. It makes these terms that were already into code now legally required. So it really is an important time for civil engineers. They got to be aware of this. So it's a paradigm shift, as we said. But like I said, Freddie and Fannie have put this into mortgages. So that means it's relevant to all structures that get funding through the bank, through the banking system. Also, there's another code that's not even referenced in here that's coming out, ICC 1500. And this is an inspection criteria for commercial buildings. That's coming out in a year. There's been a draft already created. So this paradigm shift didn't just hit condos, it hit all structures and banking and insurance. Insurance rates have quadrupled. ASC 1199 was adopted in the Florida law, and they kind of backed off and said ASCE standards are appropriate. So you have different ones, and ASCE 99 is now being updated. It's going to probably come out in 2027. And in it, it has different, it's always been the standard for the CAI, the Community Association Institute, and it allows for load tests. There's a whole section on load tests. And it has a lot of very interesting aspects. It's now like 300 pages when it was about 150. And it talks about stiffness, it talks about stability, it talks about holistic assessments. There's a lot of really good information. So whether you get the old version, 1199, or the new version, which is MOP 158, they're both really good standard or good documents about assessing the existing structures. And again, it applies to commercial and residential. IBC and ASCE 7, they have capacity requirements, life safety capacity requirements. So as part of ASCE 11, you have to tell them that it has effective capacity. That's actually in the preliminary analysis. Step number one, the first thing you got to do is tell them that it has the appropriate capacity. So load testing really can give some insight into it. ASCE 7 and IBC, they have minimum stiffness requirements. They have strength requirements. They have a seismic and wind section. There's performance metrics for soft stories, for torsion, damping, displacements. There are all metrics in there that you can measure to. You can compare it to these things to give the owner or the building department some idea of the capacity of that structure. And if you go back to this issue of structural integrity and how you distribute loads effectively, and you think about torsion, if the loads are effectively distributed, torsion is going to have the center of torsion in the center. Its displacements, its deflected mode shapes are going to be equal on both sides. If you have a huge amount of displacement on one side as opposed to the other, you got a stiffness anomaly. And then if you have a low frequency response, inconsistent, there are minimums about stiffness in the code. And if you're below certain elements or certain levels, You can't even you can't design a building with below a minimum of, I think it's 75 over H. So the codes allow for buildings to be tested, and they give the parameters from which to test to. So structural performance measurements confirm these, and without testing, we got an issue. Everyone has exposure. So I think performance testing makes a whole bunch of sense for the future here. In 2022 and 2023, there were big legal changes. I spoke about most of them, but in Florida, we had SB 154, verification for structural integrity, and also the reserves. You know, that was also a really big deal. And that has continued to evolve, that law, and it still is the model for the country. One of the interesting things that came out recently this year, or I guess 2025, was another structural integrity kind of addendum to this, and it allowed for condo owners to finance repairs. And that seems like a common sense thing, but it was actually not, they were not able to do it. So now they can, a lot of these guys could not afford to make the changes. And now they can because they can finance it effectively. So that was a big game changer. As I mentioned, all these other states have structural integrity laws in one form or another, and reserve studies and reserve requirements. You know, Virginia, Delaware, California, Indiana, and these things are changing rapidly. And also a lot of cities have instituted them, as I said before. Freddie and Fannie selling guide, their selling guide has requirements with structural integrity. So these put everybody on notice. The Florida law, though, is the one that is the most operative and the one that really set the tone. And it was signed by the governor in June of 2023. So going on 3 years now, provides inspection guidelines and implementation. And if you read it, it's important to read it because all it's really saying, it's kind of saying, you know, do what's intended under the codes and standards. You know, it talks about life safety. It talks about having all of the members functioning and all these other things. And it talks about the reserves and repairs, transparency of information, letting people know what's been done. It set the precedent for all the other states. Engineer and owner requirements in the law. Inspection of load-bearing elements, walls, and the primary structural members and primary structural systems. I'm saying that slow to emphasize it. Think about it. Inspection of the load-bearing elements, walls, and primary structural members and primary structural system. So you gotta get a look at everything. The problem is most of it's covered by sheetrock, almost in every one of these buildings. So we were part of the implementation plan of this law, and we spoke during the implementation of this. There was a working group, and you could hear the engineers call up and say, "What do you want me to do? Tear all the sheetrock down?" And the working group said, "Well, no, we don't want you to do that. You got to do the best you can." Well, in their own implementation plan, they also put in load testing. So you can test these structures. So we're sitting here in a world where visual inspections have been the norm. That's been the standard of care. The law has changed, and it specifically says you got to look at every single element. And if you can't see them, you got to go to Plan B. And Plan B is testing. So it also says, to the extent reasonably possible, determining the general structural condition of the building as it affects safety, the safety of such building. So again, you can't stop at a visual. It really doesn't make any sense. So milestone inspections for Florida. The legislature finds that maintaining the structural integrity of a building throughout its life, its service life, is of paramount importance in order to ensure the buildings are structurally sound. So it's not just something where you're inspecting it. This is going to be done every 5 to 10 years. New Jersey has the ability to be as low as 5, I think. The engineer in New Jersey has the ability to say when the next assessment comes. 10 years is the standard right now. So, but anyway, the point is that this is for the entire life of the building. So doing things that are objective, documenting small damage that could turn into big damage is really important. So performance under the direction of an architect or engineer licensed in the state of Florida for the purpose of attesting to life safety. So life safety is really the code requirement for having capacity. Again, in ASC 11, the first thing under preliminary assessment, capacity, adequacy of the structural components of the building. So if you can't see them, you got to do something. You can't just sign the document without knowing. The general structural condition of a building as it affects safety of the building, including safety, repairs, replacement of structural components to the extent reasonably possible. So you really got to think about not just the state of the building now, but what it's going to be very soon. And you have to use Champlain Tower as a guideline and say, wow, in 2 years, it degraded to the point where it was triple the level of damages. So degradation is exponential at certain points. So you can't hide damage. You have to address it. You have to arrest it, and you have to understand the capacity. So milestone inspections have 2 phases. If there's substantial structural deterioration is noted in phase 1, then you go to phase 2, and you can do destructive or non-destructive testing. And I always have these pictures in my way.
Tom, let me have an attempt. I want to go back and put some context for everybody. I think I may be finding a little bit better now, and so shall I have a go at this? But you take over from me, ladies and gentlemen. My apologies. I'm not feeling well at the moment, and I thank Tom for stepping in. But there's an aspect of this presentation which I think you'll find particularly interesting, and so is that okay, Tom?
Yeah, have at it, Doctor. We're what's
Okay.
You want to take over the slides or?
Yep. I'll take them over and
Okay.
hand them back to you in a while.
Okay, I'll stop. You go right ahead.
Okay. Now, the point about this is that what we are doing at the moment is a function of what's happened in the past. Let me just there we go. So collapse prevention has been an issue for a long time. Where I got there? Now I want to go back further in here. I want to talk about what happened to bring us to the current state and give you an impression of what's happened and why it's happened. So the Renaissance in the 14th to 17th century was a link between the medieval and modern eras. They focused on classicism and looking at human potential and literature. And so you had people like Leonardo da Vinci, Raffaello, Michelangelo, who changed various things. But one of the things that happened in the Renaissance was the Gutenberg printing press. It actually revolutionized communication between people who were doing research and their colleagues. Now imagine you think of that as a parallel to what's happening today with the internet. You actually got something which changed civilization. Additionally, we had the Copernican heliocentric model. In other words, that means the sun is the center, and you can do all sorts of things. The Enlightenment required that laws be rational, uniform, and accessible. There are other things which are listed in here which went on. In the United States, in 1819, there was the first U.S. civil engineering school at Norfolk University. In a little earlier, 1747, the first civil engineering school in the whole worldwide was in France. But this is the big one. is 450 BCE. Roman law introduced the 12 tables. You have that in US law of these days. It's it's in your laws, and it says everybody has a right to certain things. They are in these Roman laws, and in the 6th century, then Emperor Justinian included these. But essentially, what we got from there is that the codes were written. The law was something which people knew what was going to happen. They could read it. They could see what was going to happen. On top, you can see this is all European as well. So the German civil code in 1900, if it's China, Japan, Greece, and Korea. The important thing, though, leading up to what Tom's been talking about, is that we have changes and influences since 1900. And we had 1900 to 1950 allowable stress design. This often led to a safety factor of 4. So we designed for composite action. For instance, different forces coming in from different places. 1950 to 1970, we had load factors, and these simply had dead loads and live loads for separating these loads out. And it was a start of standardization and awareness of dynamics as well. In 1970 to 1990, we had probabilistic design, which is the use of return periods. And we looked at structural reliability analysis. We had uniform codes started being apparent. And then 2000 to date is the sort of thing that we're talking about right now. And this one is particularly important because safety factors started when we had cast iron. And cast iron was a horrible material to operate with. So we had a safety factor of 4 in the 19th century. We used to know it in the 1960s as a factor of ignorance. Rolled steel was introduced in the 1880s, and so the bending stress safety factor was 1.7. People did a lot of analysis of those and looked at it. And actually, if you look at what we have now, then we have safety factors of 1.4. The interesting thing that we have coming in is digital twins. People think that digital twins are an excellent idea, and in fact, they give an impression of precision, but you need to be very careful. Back to you, Tom.
Right.
Doctor, thanks for going over that. So let me, if you'll get out, I'll share my screen again and get back to where I was.
There you go.
Okay, very good. And let's see, I had gone through a lot of this already. Let's move forward. Okay, I think we had gotten to this point.
Yeah.
So milestone inspections consist of 2 phases. We talked about phase 1 and phase 2. And let me put the current slide there. Substantial structural deterioration. This is a really important point, and it's in the It's in the Florida code, I think it's significant structural deterioration, but substantial structural distress, and substantial structural weakness, cracking, finishes peeling, water penetration, sagging, deflections, misalignment. In Florida, if you lose a third of your lateral capacity, you have a significantly damaged building. So this is really important too, that there are goalposts. You know what a building should be doing, how it should be performing. You can measure that. But there's also minimums in the design code of 75 over H, and this minimum here. So they kind of align together. If you lose a third of your capacity, you got a significantly damaged building. I think it's 25% reduction for floor capacity. So
Yes.
there are minimums here that you can't go beyond, or you got a significantly damaged building. So that's why visual inspections aren't really getting us where we need to be. We're not tracking this stuff. It needs to be tracked. So reports must address the following: the type and manner of the inspection, identify substantial structural deterioration, state whether unsafe or dangerous conditions were observed, recommend any remedial measures or repairs needed. So definition of substantial structural deterioration. I jumped on this one. I'm not familiar with the slide. Sorry about that. So I got ahead of it. But a reduction of 33% of lateral capacity and 25% of the load bearing capacity vertically. So there are requirements here. The New Jersey law, very similar to Florida. It also set the precedent for others. Appropriate procedures for inspecting, evaluating, and maintaining the structural integrity of residential housing. Very similar to Florida. They modeled this after Florida. Primary load bearing system means the assemblage of structural components within a building comprised of columns, beams, bracing that by contiguous interconnection form a path by which external and internal forces applied to the building are delivered to the foundation. That's fundamental to design, and it's fundamental to the term structural integrity. They all have to work together. They got to distribute the forces. The structure should behave in a monolithic fashion, and all the forces need to get to the ground, and it needs to be stable, and it needs to meet life safety requirements. So I think we went over this already. The different states, I didn't mention Georgia, Hawaii, Tennessee, New York. New York City has a law as well. Several states are exploring building inspection requirements. And as I mentioned, the ICC 1500 is coming. So we are at a point of change, and everyone's got to be aware of that. Doing things the way you were doing them, people need to become more educated about what can be done. What are the testing methods? And ASCE 11-99 and now MOP 158 provides all that stuff. They have some really 90% of that document is about assessing material degradation and structural degradation. So it's really important for people to be aware of it. And I'll be honest, of all the engineers I spoke to, nobody knew ASCE 11 unless you were into condo world. So there's an enormous learning curve needed for the industry as a whole. So the New Jersey law continued to determine when the next inspection shall be. So, if you got a degraded building, you want to do more frequently because of this issue of exponential degradation. Protocol established by ASC or other standards, again, just like Florida, they reference ASCE, provide guidance on maintaining structural integrity. So what needs to be done differently? If you have a building that's degrading like it was down in Florida, A, you got to quantify its capacity, but B, you better protect it and seal the concrete and do things that are going to preserve it more effectively. And there are a lot of things that you can do. So you have to identify new or progressive deterioration. And this is a slippery slope, because how do you know? How do you know it's, you may be the first inspector there and you just don't know what you're looking at. People are patching and painting things regularly. One thing we didn't talk about was the collapse of a building in Iowa. Most people don't know about it. It happened in Memorial Day weekend of 2023. And it was a building that was recently purchased. It was 100 years old. It had been through a big wind event and it had serious signs of degradation. They didn't respond. The city got sued for $100 million for negligence. And that's because there were signs of deterioration, but they didn't do anything about it. So at a minimum, you can monitor things and make sure it's not changing. More aggressively, you can put up shoring and all kinds of different things. We've had instances where we were in charge of a building and we said, everybody out and let's put up shoring because this is unsafe. So that is within our purview as engineers. The inspector is exempt from liability if they follow the ASE guidelines. So you need to know what the guidelines are. If you look at just a preliminary analysis, you've got to go through an understanding of capacity, damage, and other performance metrics. It's listed very clearly. So the post Champlain Tower collapse in 2021, Florida's first condominium law came in 1963, Statute 7 and 18. 1.5 million condo units are in Florida now. I think it's 23,000 developments. So it's quite a big market. A survey in 2022, about 1 million units are more than 30 years old. So, and most of them are along the coast. So that's really alarming in that, those are pretty tough environments where you have wind risk. You have a lot of these things were built with beach sand. That is a little discussed reality that could be a big factor. And they're reaching a critical age, so they've got to be understood and tested. Miami-Dade and Palm Beach, 74% were built before 1933. So you have the Art Deco area down in Miami. So that's interesting. Inspection had been required every 40 years. The new law requirement is after 30 years. It's not every 40 years. It was after 40 years. And now it's actually between 25 and 30, depending on how close you are to the ocean. Florida and Southeast operations for reserve estimates, more than 50% weak. I'm not sure what you mean by that, Doctor. Florida.
What that is, the company, Florida and Southeast, looked at who was producing a reserve estimate, and they decided that they were weak if less than 30% of the required reserve is available. And they also found that 50% of the buildings that they looked at, the condominiums that they looked at, were actually weak. 50%.
Yeah. Yeah. So so they don't have enough money to fix them and they're degrading. So that's really what the bottom line is. Champlain Tower was significantly underfunded. Very interestingly, they redid the foyer. Like everybody wanted the foyer to look good, but they didn't fix the structural issues. And that is the challenge for engineers. You have people who are in charge who spend the money and they want it to look good, and they don't believe it's ever going to collapse. And it did. It's a shame. December 31st was the requirement to complete milestone inspections. And I think it may have extended that, Alan. I'm not positive.
Carry on. It's in there.
Oh, okay. Changes in Florida in 2025, structural integrity and reserves. Milestone inspections now limited to buildings with at least 3 inhabitable floors. So we knew that. Architects and engineers and contractors must declare a conflict of interest. This is what I was mentioning about that. This was the new law that came out. Local enforcement must report to the state. So the building department's got to upstream this information. Structural integrity and reserves can be funded through assessments, loans. This is a big deal, or lines of credit. So that was something they couldn't do, and this actually gave them a big lifeline. Uninhabited buildings reserve funding can be paused. 4-family dwellings do not require structural integrity reserve study. Associations existing before July 1st, 2022 may delay structural integrity reserve studies up to December 2025. SIRS delay associations completing SIRS studies may delay for 2 years. So it gave some relief. There was a lot of complaints by all these condos who said, we have older people who aren't liquid with a lot of money. We need time to get this stuff together. We never had an engineer. a lot of people just kicked this can down the road. So they did what they thought was reasonable to help extend this. But the good news is they can finance these things and push them out over time. And what it does, it doesn't let them off the hook on the requirements. The secret thing is you still got to do the proper assessment. You got to do the proper understanding of the structure's capacity and potential life. You got to make sure structure integrity is maintained, and then they got to have reserves. Milestone inspection of structural components by December 2025, which the building has a certificate of occupation on or before July 1st, 1992. For buildings less than 30 years old, the milestone inspection is required by the year the building is 30 years old. And if you're closer to the water, it's 25. Applies to building of 3 stories and taller. Inspections are required every 10 years after the initial milestone. Municipalities may require inspection after 25. There you go, closer to the water. Associations must forward copies of the report to all owners within 45 days. For us, we do a lot of testing, and they have a requirement. If you do non-destructive testing, you have a 1-page cover of that report that goes with the inspection. So there were considerable problems after the change in law. The monthly payments increased, insurance rates increased dramatically, costs skyrocketed, and property values went down. So this was a big shakeup and wake-up call, but it was really necessary. It was being quite irresponsibly managed. People were, you had people on the board. I can tell you firsthand experience, we were dealing with one board, and 7 out of 8 people wanted to move forward on some very pragmatic aspects. And one guy said, I'm moving. I don't want to spend a dime. And I don't want our reserve requirements to change. I'm fighting all the reserve requirements. So it's really interesting that one guy can be the cog in the wheel. And that's why they had to put it into law, because people who were not qualified to make these decisions were the ones who were restricting the things getting repaired, and it puts people at risk. So engineers have a much greater requirement now and a lot more liability. And that's why testing makes a lot of sense. To have objective information to validate your assessment reduces your liability. Milestone inspections are required immediately.
Let me jump in there, Tom. Yep. If you actually missed one of these deadlines, then a milestone inspection is required immediately, and there is a concomitant legal liability to the association. So normally, if you get a notice about milestone inspection, it must occur within 180 days. Back to you, Tom.
Okay. Structural integrity assessments procedure. Stage 1, visual inspection. So in Florida, they have a very prescriptive sort of visual inspection, a big checklist. And that was the biggest checklist I saw out of any state. But so you go through that first, and you establish the assessment area and the consequence area relative to an influenced area. So you're basically doing a walkthrough. You're not getting into every apartment. You're looking at the common areas, and you're making an assessment. You're assessing the area, the influenced area, the load path consideration, the consequent areas, signs of damage. So, but realistically, a lot of it's covered up with sheetrock. So you can't see all of it. So what is not reasonable, inspecting every structural element, assessing all structural elements, assessing structural integrity using visual only inspection, and using engineering judgment only. You can take a risk and look at a newer building and say, I feel pretty comfortable with it. I'm going to use my engineering judgment. Engineering judgment is a legitimate defense, I guess, but you also are conflicted with the requirement to validate assumptions. So an engineering ethical requirement is to validate your assumptions. So if you have any reason to not be sure about it, you can test it. ICC 1500, there's, as I mentioned, a draft out. It's the same sort of thing. When you have damage, you got to take some additional action. And what is that additional action? Well, it could be testing, it could be repairs, it could be a lot of things. But, having some cracking isn't necessarily significant damage, or it could be very significant damage in the way of the Champlain Tower. You have to, that's where your judgment comes in. And when you have damage and you don't test, you take all that risk. So there's it really does change the landscape for the engineers. So the milestone can consist of two phases. If a substantial structural deterioration is noted in phase one. So one is visual, two can be destructive or non-destructive. Didn't I already do this? I thought I did this. I think this is a double slide, Alan. The intent.
Okay, move on soon.
Yeah, yeah. So yeah, maybe these are doubled up. Structural integrity assessment, signs of damage, vulnerability, warning, damage, defect, distress, deterioration. They're all common terms.
And in fact, this is a categorization. If you go in to take a look at a building and you're doing a visual inspection, this is the sort of categories that it's moving towards deciding on which of these categories your building actually appears in. So you have to decide. You have to know what the definitions is in each of these categories. In fact, they're being discussed at the moment. I'm sure that they will come out, but nevertheless, this is an idea for you of what the ASCE is moving towards.
Okay. We are left with a series of problems. Legislators have rushed to provide laws that will make condominiums safe, especially in Florida. What exactly is safe to human occupants? Design assumes a level of risk is acceptable, but when that risk changes, we need to understand it. How can inspectors decide on safety or the level of safety? The environment is changing. Is the current assessment style going to provide us with acceptable safety? This scenario has been repeated many times. They can legislate it, they can change standards and codes, and they can find a scapegoat. So structures don't
And in practice, if you look at what happened with the Tay Bridge, the Astronomer Royal was also the designer, and they just said, no, it's all your fault. It fell down because of that. The fact is, we had all sorts of increase in knowledge of how the wind was, knowledge of fracture mechanics, which occurred. But nevertheless, he was the scapegoat, and he died in penury. And only 100 years later, we found out that actually he did everything that he could, but it was no salvation. He was still the scapegoat.
Yeah. So anyway, we just got to do the things that we need to do. Follow the codes as best we can. When you're not sure about something, get additional information, validate your assumptions. And there's an inherent risk out there, but you got to quantify it. So these are interesting slides that Alan took many, many years ago.
Let me come back in here, Tom, because there's an important point in this. These are scanning electron microscopes studies of concrete. And next slide. You can see the aging process occurs at a very small level. If you look at this scanning electron microscope of concrete sample taken from a building in Hong Kong before a typhoon, you can see that there are needle-like constituents in the cement paste. Next one. After a typhoon, look at it. It's totally different. The broken needles occurred. The chemical composition of the concrete changed just because of high stresses in that area. Next one. So the point that we're making here is we look at this sort of thing. modal force and modal displacements, and we do experiments in the laboratory. We use Young's modulus quite often, but there is no such thing as a linear elastic range. It's a good approximation for what's going on, but when you look at those scanning electron microscopes, you see that down to micro level, there's an awful lot going on. And there are indications of damage which occur, aging which occurs in the structure over a long period. And of course, this is what we do with a stress strain type of diagram. Next one. So we actually have to look at what the demand forces are and what the capacity of the structure is. And we have to establish the capacity to demand ratio. And if our approach to finding out integrity of a structure focuses on that capacity to demand ratio, we can tell what the ratio is of the risk that we have in operating a structure. Back to you, Tom.
Okay. So as I mentioned before regarding ASCE 11, they had a holistic load testing. And there's different ways to do it, directly applied loads. That's what Alan Geary did with his team at the BRE. They actually created a vibrator system and dialed that loading to 1,000th of a hertz and applied it 1 ton of force to a building and shook it at resonance. You can do proof loading, dynamic load tests, in situ loading, and comparison with prescribed criteria.
Proof loading is actually testing a structure to see if it will withstand something which is a little bit more than is required in the code. 10%, 20%. The Chinese are doing that right now.
Okay. So condition assessment, watch, advisory, and warning. Doctor, why don't you talk to that? That's
Well, in fact, these are 3 categories. If you go in and look at a structure, then there are 3 categories that you will put that structure into. So watch means it's okay for the moment. Advisory, will we find something that is worth looking at? A warning, there's something important. You need to do something about that right now. So basically, there are 3 levels that you're being asked to look at and assess the structure.
So load testing, laboratory testing, and in situ testing. So very interestingly, if you look at load testing and you go on, say, YouTube or Google, something like that, and you look for videos of that, a lot of it is static load testing. There are a lot of people out there doing dynamic analysis. A lot of the bigger firms, Thornton Tomasetti, they have a testing department. Wisgeny, Elsner, they do all kinds of testing of structures. So there's quite a lot of people who do all kinds of non-destructive testing. But you can test materials in the lab, but you can also do in situ testing. And you can test the entire structure for its response, which is one of the approved methods. So you have laboratory testing, and you'll take a specimen and you'll put a load on it and look at how it displaces and get the force displacement relationship. Everybody, I think, who's an engineer is familiar with doing some of that. This was what Alan did at the BRE, looking at how structures respond. He took this counter-rotating mass that created a ton of force linearly, put it on the building and shook it at resonance and took measurements of it. We have some of those reports on our website. Fascinating body of work that's never been repeated. He did 40 full-scale structures. If you look at some of the other people who did vibration tests like this, they might have done a handful. over their entire career. But Alan did 40 of them, large dams and smokestacks and buildings all over the UK and Europe. So quite an interesting body of work. The assessment of
Now,
capacity and risk.
if I can jump in here, Tom, no, that's okay. What are forces is the whole idea. And the first thing is the linear elastic range, only lasts for a little while, and then we have ductility. And if we put a capacity diagram, we find what the response is at resonance, then we can have the displacement per unit force, and on the right-hand side of the equation, we have zeta, which is the damping, F squared, which is the frequency, M, which is the mass of the structure, modal mass of the structure. So we can actually assess what the structure is, what the risk of a structure is by using this equation, displacement per unit force. Instead of using a force and finding out what displacement we go to, we find the displacement per unit force in much the same way as Hooke and Newton envisaged. So we're doing that now. We can do that. We can use a number of different things. Okay, next one.
Okay. Yeah, to talk to this just for a second, though. So displacement is a function. If the force is over here, you have force divided by damping and frequency squared. So this displacement under the same force is a function of the square of the frequency. So if you measure that, you're going to have a good idea of the overall stiffness. This is a proxy for stiffness. And then damping is directly a component of this equation as well. So, but it's really important to realize that there's a squared relationship. So as you lose stiffness, you're going to get a squared relationship with you're going to get much greater displacements. So what does that tell you? When you put this into a fatigue analysis and you start looking at how many cycles take you to the end of your fatigue life, and you have a much softer structure, you're going to have much fewer cycles. It's going to degrade exponentially more. So that's a really important item to add to this these list of slides, Alan. We should have a fatigue slide in here. I gave that, I showed that yesterday. But then now you can understand what the risk is, right? Your measured performance compared to what you expect. You know, the displacement per unit force relationship of a well-built structure is going to be X. And as these parameters change, that displacement per unit force relationship is going to change accordingly. And then you have factor safety requirements, and that gets you into your risk. So in any event, taking measurements as it relates to force displacement can give you an idea of what the risk profile of a structure is. So structural health monitoring in the future, high-tech approaches, self-repairing structures, and repairing damaged structures. So what we're doing now, self-repairing structures would be interesting. We'll see how that evolves. But
well, the Romans had a type of cement that was actually self-repairing. Yeah. They found an additive that they could put in there. We seem to have forgotten about it, though.
Well, so volcanic ash, Alan, we can't really get that too readily. So that's one of the big problems. Philosophy, natural principles. So Newton's second law of motion. Alan, do you want to speak to this?
Force equals mass times acceleration. And that started off with Newton and his laws of motion. And this one, force equals mass times acceleration there. So if we look at how a system is going to behave, then it will give a displacement and then an equation on the right-hand side. In fact, if we take F across to the other side, then what we find is that we've got displacement per unit force, but it's the same equation. So there's nothing new in there. but we can go directly to displacement per unit force so long as we can measure damping and frequency. So if we can measure those, we can look at what the capacity of a structure is compared with what we expect it to be. The other thing here is that statics is just a special case of dynamics. So we take Newton's second law of motion, we have that equation, but the bottom right is the curve which this gives you, a dynamic magnification factor, which occurs if a structure is behaving inside its resonance. So we tend to look at things in terms of statics, but dynamics is important, as we've seen in all sorts of ways. Next one, Tom.
Well, I think the important thing, I just presented on this yesterday, was that there is no statics. Statics, it's the dynamic equations, and statics is just when the frequency goes to zero. So we're misleading people. We're actually developing a tech lab that can help people understand, starting with the equations of motion and looking at statics as a unique case of dynamics as opposed to an alternative methodology. Because I think there's been damage done to the engineering community. If given the choice between doing a dynamic analysis or a static analysis, you just say, I'm going to do a static analysis. And I think there's a fundamental belief they're different, and they're really not. They can be performed differently, and they're more simple, and that's why people choose it. But dynamics are the fundamental science that apply, and understanding them is really important. And then when you understand them, then you can apply them. Undergraduates don't get a background in dynamics, but it's important that we teach this properly. So. Indicators of damage using dynamic load testing, changes in frequency, changing in damping, mode shape anomalies, modal ratios. And what modal ratios are both the ratios between the frequencies and also in the amplitude between different measurements. And these are things that we look for in dynamic analyses. But as these things change, it quantifies the overall change in signature, which represents the entire stiffness relationship within the structure. And then there are also things without a spectrum, Alan. We probably should have had a spectrum for this, but bifurcation.
It follows just after.
Okay. So indicators of damage using dynamic and natural frequency, future approaches. Use of AI requires data from many locations, requires automatic analysis, identifies where maintenance is needed, self-repairing materials, the Romans did it, identification of changes in aging, identification of damage caused by various sources, environmental, wind, wave, action, earthquake, flood, malintended people, impacts, and the like, warfare, accidents. The thing about AI is that AI is going to have a very large impact in the world. Taking dynamic measurements on a structure, if you can do it quickly, we can do it in a day, gives you the ability to physically measure it. If we're going to rely on AI as a tool for engineers, and it's going to get involved and already has in design, we need to check it, so we need to have checks on AI. I personally find that AI has a lot of problems and makes a lot of mistakes. So we got to be careful. We got to just check its work.
Absolutely right. And in fact, the slides which follow talk about this. Digital twins, effectively, people are talking about that as though a digital twin will tell you everything about a structure. It won't, because it depends on how much the person doing the analysis has actually put in to that digital twin, that finite element program. And in practice, there's an awful lot that can go on. And we've found differences from measurements of 500, quite often 50% difference from what we actually measure.
Well, and the other thing is, Alan, if you create a model and you think it's going to be there forever, but the structure is degrading, you need to have a way of calibrating that degradation. And
Exactly right.
so you have to take measurements. So AI and high tech information from all over a structure. Instruments are inserted at the time of construction. Holistic analysis assisted by modal analysis and fracture mechanics. Um, Comparison of structure with mathematical model. And that's a really important thing. Calibrating a model is a really important aspect, as we were just talking about. Automating analysis of various locations, automatic warnings of changes to the structure, and identifying what if future behavior. So looking at potential risk scenarios and understanding if you can withstand them. So this kind of ties right into the concept of sustainability and resilience, which is broadly applied, but there's really no metric. And through dynamics, you can create a metric. So how are dynamic measurements taken? Well, to get a holistic analysis of a structure, you just put sensors on the top and you validate how the structure moves back and forth into different directions. You get higher order modes, vertical modes of the structure. You're also measuring from up here how the structure behaves in its geotechnical conditions. Again, there's a standard on this, ISO standard about evaluating structures. It generally takes about 3 to 6 hours to get the dynamic characteristics. The first pass is in 1 to 2 hours, and you can just get at least an understanding. You may not be statistically correct, but you can get an understanding of some of the dynamic characteristics. And data can be processed quickly. It's non-invasive and non-destructive. So these basic techniques already exist, and they existed back when Alan was doing his work for the BRE in the 70s and 80s. We're just technology just allows his $200,000 analysis to happen in hours at a tiny fraction of the cost. So the forces are provided by the environment. They're just ambient forces. The instrumentation includes Wi-Fi, embedded sensors, signal to noise ratio that has to be appropriate, microchip devices, MEMS. So they have very sensitive MEMS devices now that are much less expensive. So on every level, the processing, the equipment, every aspect of it has gotten more efficient. The analysis techniques include modal analysis. And if you're not familiar with modal analysis, email us and we'll send you a link to some websites. Modal analysis is an incredibly powerful tool. They do this on the Artemis rocket. They do it on the space shuttle. They do it on large ships. They do it on tall buildings and do it on long span bridges. But you can do them on all structures and you can do it efficiently. So in any event, you're looking at stress on a micro scale and you're applying fracture mechanics. And we talk about PPV as a metric for vibration monitoring, and it's not very accurate for that sort of a approach. But modal analysis gives true displacements of a structure, frequency content that can be measured and monitored for the life of the structure. So with mathematical modeling, finite element modeling, they can be very inaccurate. Alan mentioned 50% inaccurate. We had seen models, Alan, we did a bridge where it was 500% off. The
Yep.
assumptions put into a model, there were 62 assumptions. And if they're each 10% off, you're going to have an enormous amount of error. And again, you're using engineering judgment. What's the E value for the concrete? What is the strength of the steel, and what's the connection doing? So they can be calibrated with real measurements. Alan, I think we have a 2 hour thing. What do we have, about 39,
What
4:39
time do we need to finish, Tom?
at 5 o'clock? And yeah, I just wonder if we have too many slides to go through.
We have 20 minutes to go.
Yeah, how many slides are left, do you know?
Okay. Oh, quite a few.
All right, well, we want to finish them. So I'm going to try and move a little quicker. So
Well,
forces,
this section is how can we use a force? In other words, how can we do this holistic measurement of the integrity of a structure? First of all, we need a force. So how are we going to create that? Next one, Tom. This is the Van der Hoeven spectrum of wind forces operating between one cycle every few days up to one cycle every 10 cycles per second. And on the right-hand side here, we've got normally what occurs in practice, and there is the spectral gap. In other words, there is an area where there's not too much wind, but then there's a peak which will give us one cycle every 2 days. There is a peak of one cycle every 4 days. In other words, if a system is going through past a point on the Earth, it will on average take 4 days to pass by that point. So in other words, we've got a well-behaved spectrum which we can use. We don't need to do anything very much apart from use the wind. We've got all sorts of forces which, next one, Tom. Next one. And this is what we do to produce our model. We have effectively, we're using the second law of motion, mass times acceleration plus stiffness times the displacement differential between floors of a building equals the force, F3, which occurs at that. You put all these together, and now you understand completely how to do a mathematical model. You can do that quite easily. Lots of systems have these available for you. But the thing that is missing is damping. And actually, damping is an indicator of energy loss. And energy loss occurs when you've got a problem with a structure. So in other words, yes, you can do this through finite elements, but additionally, you need to look at the damping as well. Next one, Tom.
Okay. Well, the issue of damping, I want to clarify. There's the Japanese code actually separated them out very nicely. You have structural damping, you have, radiant damping into the ground. You have all kinds of different levels of damping. Structural damping is something that can be measured under ambient conditions. Overall damping can include a lot of sources that are force-driven and they're response-driven within the structure. So being able to separate them effectively and measuring structural damping effectively is really a powerful tool because it becomes a proxy for damage detection. Okay. So what is a force? Any action that tends to maintain or alter the motion of a body or distort it. What is an action? Wind forces created by differences of pressure in the atmosphere, earthquake. Fault comes unstuck and generates vibrations, and flooding forces caused by moving mass of fluid. And and they're all dynamic forces. They all create dynamic events. Even wind, even if you have a steady wind, it comes in a frequency band, and we deal with that all the time. So that it's a very much a dynamic force, not to be confused with static analysis in any way. Another thing about wind forces is, you have a gradient of those forces where you get zero velocity down here, and you have a boundary layer until you get up to the higher level. So that's very relevant to structures as well. Alan, what's the what do you have here? This lava lamp of forces.
Oh, that's what happens in the ground.
Oh, okay.
If you look at a single point there, look for a long time at a single point, and you'll see it doesn't go anywhere. But there are waves passing through the ground, so that occurs in earthquakes. And of course, earthquakes don't last very long, but wind does last for a long time. So you've got the wind forces, you've got the Van der Hoeven spectrum. You are able to use this as your force going into a structure, and that will allow you to find what the displacement is per unit force of the structure.
Okay. So some common force generators. Well, we got some big wind and flooding and earthquakes. And I guess
But they're not usable. They don't last for very long.
you know, how do we measure forces? Again, Newton's second law. We can't get away from Newton. You want to explain this, Alan?
No. Second law is what we use for the measurement in looking at response of a structure. And that diagram that Tom is showing at the moment is a very easy way. It's used in MEMS accelerometers as well. So you can use that. Technology is improving, and that is now becoming miniaturized, and you can do all sorts of things with it.
Well, yeah, to add a little clarity, that instrumentation is becoming more and more automated, and we can put sensors in structures. We can put them on for hours and take measurements and do modal analysis and things like that. So, using instrumentation should be done broadly, and just to take the guesswork out of these assessments. So, your induced vibration tests, Alan, very interesting. Um, I'll take a stab at this if you don't mind, because we kind of
Sure.
talked about this already. But the importance of this, we have it on our website. But what Alan was doing was imposing a force on it and showing how frequency changed at low amplitude, and what the amplitude was and what the percentage damping was. And here's that damping curve right here. So what he did was he excited this structure and stopped the vibrator. And so you had the force that started to decay, right? And the building started slowing down in its vibration. And he measured the change in damping. And what was really interesting, it went from 2.65 at 10 times the amplitude down to 1.37% damping at a relatively modest amplitude. And the frequency likewise changed. It went from it got stiffer as it went on. So there's a nonlinearity associated with this. Damping changes significantly, frequency changes a bit. Now this is well within the elastic limit. So it's really important to realize that both of these elements are non-linear, but they can be measured, and how non-linear they are within the quote unquote linear elastic range is very relevant. If you got a lot of damage or you have a fundamentally non-monolithic structure, those non-linearities are going to be quite broad, and you're going to see quite a lot
The
of
interesting
difference.
thing, though, in this series of tests was if you use second law of motion and you calculate what the mass of the structure was, despite all those nonlinearities, you get the same value, plus or minus a little bit, at all of the stages of testing. Now that's an indication that this was working okay, and the measurements of frequency and damping were okay as well.
So yeah, that became the check because you knew the mass wasn't really changing. It could change a little bit, but it really wasn't changing too much. So you knew mass was a constant, and you put it into that equation, and you knew what your force was because you're applying it, and you knew what the frequency was because you're measuring it, and then you saw what the amplitude was, and so you knew the displacement, and you could measure the damping as you did decay. And again, your mass was the check. So very interesting body of work, never to be repeated. So here's one type of monitoring device. This is a German monitoring device. Doesn't have a great noise floor, so you can't do a lot of short buildings with it. But so here we are again with this, Alan. I don't know why these are in here. Um, So some classic strain gauges. I think everybody has seen these crack gauges, but at a minimum, like the Champlain Tower, when you have such massive cracks, you got to do something. You got to know if that structure is moving and degrading. At a minimum, these are $10 each. Doing a modal analysis and understanding capacity is important. Cracks can expand, they can move thermally, they can move due to moisture. But for the most part, especially this one happens to be in a basement, um, you know, looking at them can give you some idea if something's moving. It does give you two axes too, so you know if it's moving up or down or
Tom,
laterally.
there's a point to be made here. Perhaps I can take over and put some sharing on here.
Sure. You go ahead.
Okay.
You gotta.
Now, this is the future. This is where we can have a new device which is battery operated. It can run on solar input and it connects directly to the cloud. And because of that, a report of the structure can be performed very quickly. If we go into what Tom was saying, we can have not just this old type of crack gauge, but we can use accelerometers on either side of a crack. And when you do that, you see in 3 dimensions and to a level of 10 to the minus 10, 10 to the minus 12 of a meter of what's going on inside there. And then we come back to those scanning electron microscope, electron microscope studies. We actually see if a crack is occurring at very small level. Oh, sorry.
You're like at 80 something, Alan.
Yep.
Yeah.
So how large does a crack need to be to cause concern? Is it a load-bearing member? In a load-bearing member? Is it confined to the surface, or is it telling us about the behavior lower down inside the structure? Do you need to test for the depth of a crack? Do you need to test the member which has a crack? Does it have implications for load carrying in a wider area? Does it indicate a holistic problem to the structure? So in other words, what I'm saying here is the very simple device of several $100s will tell you in broad terms what the crack width is going to be. But there are different aspects of a crack which are important to a structure. And now spectra. We can tell a lot about what structures are doing using power spectral density. And we have other types, of course, acoustic spectra, electromagnetic spectra, and spectrum of human behaviors. This is one which occurs just in a structure taken in both the north-south and the east-west. You see changes in that, and you see lots of modes of vibration as the structure behavior becomes more complex. You can do that, and they actually will tell you this sort of thing. A peak in the spectrum will be an indication of the structure wobbling. And it can be, as the frequency goes up, it gets more and more complex. There's lots of things that you can tell. You can tell what the tilt of a structure is using an accelerometer. And the reason you can do that is that statics is a simple case of dynamics. In practice, if you have a device which is tilting over, an accelerometer will tell you what that is. And there we go. If you are able to resolve down to zero frequency, then what you get is that kind of thing coming out. You can have indicators of damage. On the right-hand side here, we got spectral bifurcations. In other words, the structure here was jumping from one frequency to another. And so if you look at that, you can see it's a lot wider than one without spectral bifurcations, which are occurring there. Modal diagrams. You can tell all sorts of things that occur. On the right-hand side here, we have a building in which we have one space in the area of 28th floor in which there is much more movement than in other places. So this is a fundamental mode of vibration. We're looking basically at a simple straight line mode. And you can see that in that case, there's something that we should be looking at. Fundamental modes. We look at those mode diagrams like this, and they tell us that the structure is moving from side to side. And we have unusual occasions that we find all sorts of things going on. We can find that the modal ratios may over time change. And if we've taken a baseline and we look at that, then we can see what those changes are. And the big one is looking at damping. And you can see a reasonable damping curve. In other words, we've got amplitude and damping there, and another one in which there's a lot of scatter. If there is a lot of scatter, it means that energy is being dissipated at various amplitudes. And if you use fractal mechanics, you can see what that means. In this particular case, we can use a risk ratio. We use those equations that I showed you earlier, and they will actually give you an idea of what the capacity of the structure is compared with what was expected of the building. And with this, we can actually find a risk ratio. I wanted to say one more thing. I'm going to press on here. A building in Florida that we looked at. You actually look at um, 10 of them constructed at the same time. They were 50 years old, and their capacity, measured with the method that I've been talking about, varied from 37% up to 72%. Why? They were close to water, and that actually tells you why some municipalities have decided that you must have a 25-year period between doing inspections of structure. Um, Ladies and gentlemen, I would just like to finish up by coming back to this 12 tablets of Rome. There is a direct line through in the law what they produce and what we produce these days. And in practice, you have in the United States the conditions for people in there, and that was first produced in Rome 450 years BCE. So we have things to learn, and we can. Tom, over to you.
All right. Well, thank you, Doctor. And everybody, that's all that we have for this presentation. And sorry for the choppy start and the way it kind of evolved out. But are there any questions about structural integrity and dynamic assessments by anybody? Let's see if we got anything in chat. So we don't have any questions in chat. I guess that would be it. So with that, we have everybody's name here, and we can reach out to people if necessary. But certainly put something in chat if you had any questions, so we can circle back with you if necessary. Let's see. So there is
My apologies for my health problem, and my thanks to Tom for standing in there. If you're in doubt, though, read through what the presentation has in there. There's lots of information which are very interesting for if you're looking at the structural integrity of a structure. Thank you.
Okay, very good. All right, signing off. Bye-bye.